In the Week 2 Foundations of Physics lab, we were given the task to create a motor using only one battery, one short length of wire, one small circular magnet, and a screw. Our initial understanding of motors was that a motor is any device that converts electrical energy into kinetic energy. Often, this kinetic energy comes from the act of rotation. We also knew that the function of a motor was related to magnetism, whereby the spinning of a rotor results from alternating magnetic attractions which continuously push and pull opposing sides, thereby inducing rotation. Judging by the given materials, we presumed that the electrical energy source would have to be the battery, and the spinning object was likely to be the screw. We also knew that in order for a motor to function, the circuit would have to be complete. That is, that the electricity leaving the battery must eventually re-enter the battery. We began to play around with the materials, keeping these considerations in mind. We tested each possible order of arrangement with the magnet, screw, and battery, ensuring that every time the wire completed the circuit. This initially yielded no promising results. All we got was some small sparks, a bit of smoke, and a pretty intense warming of the battery. Eventually, we found that the screw could be made to hang from the battery if placed between the battery and the magnet. When completing the circuit by connecting the wire from the battery to the magnet, the screw and the magnet began spinning. We tested this again using the opposite side of the battery. Interestingly, this still worked but caused the screw to spin in the opposite direction. We also found that flipping the magnet also caused the spin direction to change. Now that we had a functioning motor, our next goal was to determine the rotation speed. Using a whiteboard marker, we made a thin mark on the circular magnet and filmed its spin with a slow motion camera. Over a 7-second time period, we counted the number of times we saw the thin mark appear and disappear. This would give us the number of times the magnet rotated over the time period. In total, we counted 109 rotations over the 7 seconds, which averaged to 15.57 rotations per second, or hertz. Now that we had not only a functioning motor, but one whose rotation speed could be predicted, the next question we asked ourselves is, how does this actually work? First off, there are 3 important things to consider when looking at this motor: the electrical current, the magnetic field, and the force which pushes the screw. While it may be intuitive where the first 2 come from, it is not immediately obvious where this mysterious force comes from. This force is what physicists call a Lorentz force, and arises when an electric current and a magnetic field meet at perpendicular angles. The direction this force points to is determined by what many call the right-hand rule. In our motor, the electrical current travelled from the positive terminal of the battery to the magnet, and the magnetic field extended from the north pole of the magnet to the south pole. At the point of contact with the wire, the current vectors and magnetic field vectors were perpendicular. To the right side of the magnetic field vectors pointed right, so by the right-hand rule, the Lorentz force pointed outwards. To the left, the magnetic field vectors pointed left, so again by the right-hand rule, the Lorentz force pointed inwards. These opposing forces on opposite sides in turn caused the magnet to spin. Flipping the battery meant the magnetic field vector stayed the same, while the current vector now pointed in the opposite direction. By the right-hand rule, this produced Lorentz force vectors with opposite direction to the previous example, in turn resulting in a rotation in the opposite direction. Flipping the magnet meant the current vector stayed the same, while the magnetic field vectors were now reversed. This similarly produces Lorentz vectors with opposite direction, in turn causing the direction of rotation to change.